Hello friends, welcome to 10th Standard Maths chapter number 1 Real Numbers topic number 2. In previous lecture we discussed about Euclid division lemma and division algorithm, as well as we also discussed about Euclid division algorithm, Euclid division lemma, exercise 1.1. This all we discussed in our previous video. If you missed that video, you can follow the link given in description and you can see that video. Now today that is Fundamental Theorem of Arithmetic. Before start this theorem or this topic, I have some questions for you. What is prime numbers? What is composite numbers? Right? So prime number is a number with exactly two factors. Means a prime number have only two factors, a number itself and 1. For example 2. So 2 cannot further divide. Okay? You can say 2 ones are 2. Am I right? So the factor of 2 is 2 itself and 1 because 2 ones are 2. So 2 is the prime number. Am I right? Likewise 3, 5, 7, 11, 13, 17, 19. So these all are the prime numbers which cannot divide further. Okay? And it have only two factor, number itself and a 1. Now what is composite numbers? So a number with more than two factors, because prime number have a exactly two factors, so every number have a exactly two factors are there, number itself and 1. Okay, but if the number have a more than two factors, then it's called as a composite number. For example 4, right? 6, 8, 9. So 9 have a number itself and 1. So 9 ones are 9. Okay. So it have a two factors, 9 and 1. But also you can further divide it, 3 threes are 9. So one more factor is there, that is 3. Right? So the factor of 9 is 1, 3 and 9. Okay. Likewise 4, 2 twos are 4. So the factor of the 4 is 1, 2 and 4. Okay. I have one more question. What about 1? 1 is prime number or composite number? So the answer is 1 is neither prime nor composite. So you can't say 1 is the prime number or composite number. Is that clear? Now let's some more example of composite number and going to in detail in composite number. So these are the example of composite number 4, 6, 8. Am I right? These are the example of composite number. So you divide them, 2 twos are 4. Okay. So the factor of 4 is 2. Okay. Next 2 threes are 4, 6. Okay. 2 fours are 8. 4 is further divided into 2 twos are 4. Right. So these are the factors of that numbers. Okay. And these all are called as a factor trees. Right. 4 is divided into 2 and 2. 2 twos are 4. So these are a factor tree of 4, factor tree of 6 and factor tree of 8. Right. Now by observing this leaf of the trees, you conclude something. Look at the leaf of that factor trees. By observing that, you can observe that or you can conclude that these all are the prime. These all numbers are prime numbers. 2, you cannot further divide it. 3, you cannot further divide it. So in the leaf of the factor tree you always got a prime number, right? And these are the product. So can I say that composite number is the product of prime numbers, right? So can we say that prime number is building block of composite number? So by product or by multiplying the prime number, you got the composite numbers. Am I right? So the answer is a big yes. Yes, you can say that a prime number is the building block of composite number, or the product of prime number always give you a composite number. Now further analyze the composite number. This is 6. Okay, so I factorize that. 2 3s are 6, as well as you can also say 3 2s are 6. Okay, is have any different other than order? No, na. So it have a no difference. 2 3s are 6 and 3 2s are 6, both are same. So order doesn't matter, right? You can't say that these are the different things, just order is changed, the result will not change because the product cannot be changed, right? The order of the product did not affect the result. So now move to the fundamental theorem of arithmetic, and this is the statement of fundamental theorem of arithmetic. Every composite number can be expressed as a product of primes. Every composite number can be expressed as a product of primes, right? 2 3s are 6. So this is the product of 2 and 3, and 2 and 3 are the prime number. And this factorize is unique apart from the order in which the prime factors occur, and it did not affect the order in which prime factor occurred. Means before 2 is occur or 3 is occur, doesn't matter about that, is not affect the result. Okay, let's take one example. Example number 5 of NCERT book. Consider the number 4 raised to n where n is the natural number. Check whether there is any value of n for which 4 raised to n end with the digit 0. So friends, if any number is end with the digit 0, then it would be divisible by 5. It is the rule. Okay, let's take 10. Example 10, right? 10 is the end with the 0, so it must be divisible by 5. So any number is end with the 0, it always divisible by 5, right? So if 4 raised to n is end with the 0, then it must be divisible by 5. So now 4n, okay, 4 raised to n, so I can write as a 2 into 2, okay, because I factor 4, so I can write like 2 into 2, so 2 raised to 2, right, n raised to n, right? Now 2 is the power and n is the power, so I will multiply both the power, so I got 2 raised to 2n, right? So by factorizing this number, I always get number 2 but not get 5, right? So here only 2 is the prime number in above factorization, right? So by fundamental theorem of arithmetic, we can say that there is a no natural number n for which 4 raised to n ends with the digit 0, because if it ends with the 0, it must be one factor is 5, but here the factor is only 2. Example number 6, right? Find the LCM and HCF of 6 and 20 by the prime factorization method. Look at friend, you are not using the word Euclid division lemma or Euclid division algorithm. Here is a prime factorization method. So you have to factorize these numbers, and after that you find the LCM of HCF, right? So don't use the Euclid division lemma or Euclid division algorithm for this method. If in exam it mentioned by prime factorization method, you must follow this method, not Euclid division lemma or Euclid division algorithm. Okay, so how you start this method? So first factorize 6 and 20. Okay, so by factorize 6, you got 2 3s are 6, right? So 2 raised to 1 and 3 raised to 1, I can write like this. Okay, further 20, 2 2s are 4, 4 5s are 20, right? So I can write here 2 is number of 2, so 2 raised to 2, and 5 is 1, so 5 raised to 1. Now remember this thing, in HCF, the product of the smallest power of each common prime factor in the number. So when you find the HCF by this prime factorization method, you factorize first that number like 6 and 20. By after factorization, you have to select a smallest power of each common prime factors. So these are the prime factors, right? You have to find the smallest power. So 2 is here also and here also, right? So smallest power is 2 raised to 1, right? It is common in both the number, right? Factor, right? 2 raised to 1 and 2 raised to 2, in which 2 raised to 1 is the smallest power, right? 3 raised to 1 is here, but here not present, as well as 5 raised to 1 is here, but in this factor 5 is not present. So 2 is the only common factor which is present in both. So 2 raised to 1 and 2 raised to 2, but the smallest power is 2 raised to 1. So here HCF is 2 raised to 1, right? Now LCM, product of greatest power of each prime factor involved in the number. Now for the HCF you consider smallest number, right? But in LCM you have to consider the highest power. Greatest power is 2 raised to 2. Now 3 raised to 1 is also there, because this is also greatest power, right? And 5 raised to 1 is also available. So here LCM is 2 raised to 2 multiplied by 3 raised to 1 and 5 raised to 1. So it's give you 60, right? So this is the method by prime factorization method. Okay, by that you can find the LCM or HCF by using this method. In HCF, the product of smallest power, and LCM is product of greatest power. Remember this, okay? And in HCF you have a common prime factor, okay? And in LCM you have a each prime factor, means you have to consider all the factors like 2, 3 and 5 in LCM. But in HCF, which are the common? In both 2 is the common and lowest power is 2 raised to 1. So that's why consider 2 raised to 1. Okay. Now by observing these two, LCM and HCF, you can conclude one more thing. Let's take it. So in this, in previous example you can see that HCF of 6 and 20 is 2 and LCM of 6 and 20 are 60, right? Now what is HCF of 6 and 20 and LCM of 6 and 20? 2 and 60. So multiply both, you got 120, and if you multiply these two numbers 6 and 20, you got 120. So can I say that if you HCF of AB multiply by LCM of AB is equal to A into B, means HCF of two numbers and LCM of two number, the product of HCF of that two number and LCM of two number is equal to product of that two numbers, A and B. Alright, so this is the most important rule which we use in next exercise. So HCF of two number multiply by LCM of two number is equal to product of that two number. But remember this thing, this rule is applicable only for two numbers. Okay, two numbers is only applicable in this rule. You can't use three numbers. For example, 6, 20 and 30. So at that time you don't use these rules. Okay, this rule is applicable only for two numbers, right? Now a next example number 7 of NCERT book. Find the HCF of 96 and 404 by prime factorization method. Hence find their LCM. So you have to find the HCF and then LCM, right? So first factorize the 96. So you got this factorization, okay. Then 404. So this is the factorization. So you can write 96 factor of 96 like this, 2 raised to 5, because the number of 2's is 5, as well as 3 raised to 1 is 3, right? Here 404, 2 raised to 2, because here number of 2's are 2's and 101 raised to 1, right? Now HCF is, again remember that, product of smallest power of common prime factors. So here common is 2 and 2, and which are the smallest power? 2. So 2 raised to 2 are the HCF of 96 and 404. So that is 4, right? And LCM is, so LCM is using the previous rule. LCM is a product of both the number divided by HCF of 96 and 404, means the HCF of these two numbers. So it is 4, and product of 96 and 404 is 38,784. So by dividing them you got 96. So these are the LCM of this 96 and 40. Now example number 8. Find the HCF and LCM of 6, 72 and 120 using the prime factorization method, right? So first find the factor of 6. So 3 2's are 6. Find the factor of 72. So it is like this. And the factor of 120, right? So I can write this, 6 is equal to 2 raised to 1 and 3 raised to 1, 72, 2 raised to 3 and 3 raised to 2, because number of 2's are 3 and number of 3's are 2, so 3 raised to 2. Likewise 120, 2 raised to 3, 3 raised to 1 and 5 raised to 1, right? Now again HCF is a smallest power, right, of common number. So here 2 is there common, right, and smallest power is 2 raised to 1, as well as 3 is also common in all the three factors, factors of 3 numbers. So 3 raised to 1, 3 raised to 2 and 3 raised to 1. Again smallest is 3. So 2 raised to 1 multiplied by 3 raised to 1. So 2 raised to 1 and 3 raised to 1 is equal to 2 3's are 6. So product of smallest power of the each common prime factors in the numbers. So that is 2 raised to 1 and 3 raised to 1. 2 3's are 6. So 6 is the HCF. Now LCM. So LCM is the product of greatest power. So here greatest power is 2 raised to 3, right? Here 3 is 3 raised to 1. 3 raised to 2 is the greatest power, right? And 5 is not present in this factor. 5 is not present. Yes, here is the 5 present. So 5 raised to 1. So by multiplying this you got 360. So 360 is the LCM of 6, 72 and 120. Now we start exercise 1.2, right? First exercise 1. Express each number as a product of its prime factor. So you have to just express number in the product of its prime factor. So you just factorize them and write this. First is 140. So now factorize 140. So you got like this, right? Now just write this in our method. So 140 is equal to 2 2s are, okay, just I write it here, right? Then 2, here 2 number are there, so 2 raised to 2, 5 is only 1, so 5 raised to 1, and 7 is only 1, so 7 raised to 1. So this is only a product of its prime factors, right? So try it yourself, okay, second, third, fourth and fifth. Okay, now moving toward the next let's take next example, example number 2. Find the LCM and HCF of the following pairs of integers and verify that LCM multiplied by HCF is equal to product of two numbers. So first we have to find the LCM and HCF of the pair of the integer, and then we have to verify this formula. So first pair is 26 and 91. So now the factor of 26 is 13 2s are 26, and 2 and 13 are prime numbers, so they cannot further divide, and 13 7s are 91. So 7 and 13 is also a prime number, so cannot factorize more. Now I can write 26 as a 13 2s are 26 and 91 13 7s are 91, right? Now we have to find HCF. So HCF is the smallest power of common factor. So common factor are 13 and 13, okay, and smallest power is 13 raised to 1, so HCF is 30, right? And LCM is a greatest power of each factor. So each factor is 2, 7 and 13, because each factor, so we can cover all the factors. So 2 multiplied by 7 multiplied by 13 is equal to 182. Now we have a HCF and LCM. Now we are going to verify by this formula. The formula is LCM multiplied by HCF is equal to product of two numbers. So LCM is 182, right, and HCF is 30, right? 13 is equal to 26 multiplied by 91, product of two numbers, right? So 182 multiplied by 13 is equal to 2366, and 26 multiplied by 91 is equal to 2366, right? So the verification is right, okay. So HCF. Now we have a more examples, right? So that you have to try yourself. A 510 and 92 and 336 and 54. It try yourself. So first find the LCM and HCF and then verify it by this particular formula, right? Exercise number 3. Find the LCM and HCF of the following integer by applying the prime factorization method. Remember prime factorization method, not Euclid division lemma or Euclid division algorithm, right? So 12, 15 and 21. So we have to factorize. So factor of 12, right? 2 2s are 4, 4 3s are 12. So factor is 2, 2 and 3, right? Factorization of 15, 5 3s are 15, right? And factorization of 21, so 7 3s are 21. So I can write 12 as a 2 raised to 2 multiplied by 3, because here 2 number of 2s are 2, so that's why 2 raised to 2, 2 power of 2 multiplied by 3. Then 15, 3 5s are 15, so I write 3 5s are 15 and 3 7s are 21. Now here we have to find HCF. So HCF is the smallest power of common factor. So common factor is 3, right? Here 3 is the common factor and smallest power is 3 raised to 1. 1 is the power, so that's why 3 is the common factor. So HCF is 3, right? Now LCM. So LCM is the greatest power of each factor. So 2 raised to 2 is the greatest power in each factor. So 2 raised to 2, 3, 5 and 7. So 2 raised to 2, 3, 5 and 7, it's give you 420. So HCF is 3 and LCM is 420. You can, by factorize this type, you can also make a factorization tree like this. Okay, this is factorization tree. In some book you got this type of trees. So you can use this method also and you can use this method also. But I follow this method because it is better one and easy one. Okay, and you can also make this type of factor tree. This is called a factor tree, right? And you can use also this method and this is also allowed, right? Now next is find the LCM and HCF of the following integer by applying the prime factorization method, right? So 17, 23 and 29. Look, these all are the prime numbers, so that cannot be further divided. Okay, so the LCM is 17 multiplied by 23 multiplied by 29 and HCF is 1 because they have no common factors, only 1 is the common factor, that's why HCF is only 1. Okay, and this is the, you can use this method also, prime factorization method. Now example number 4 is also try yourself. Okay, by using this formula, you have a HCF of 306 and 657, 9. Okay, so multiply 306 and 657. Okay, and you got the product of two numbers and then you divide it by your HCF, so you got your LCM. So it is also try yourself, right? Okay, try next example, exercise number 5. Check whether 6 raised to n can end with the digit 0 for any natural number n. Okay, it is look like a example number 5 which you learn in slide number 6, right? So if you learn that properly, example number 5, then you conclude that if any digit is end with the 0, then it must be divided by 5, right? Now if the number 6 raised to n for any n where end with the digit 0, then it would be divisible by 5. Yes, like this all are discussed in example number 5. Okay, now factorize 6, so 2 multiply by 3, right? So I factorize them. So here also the prime factor is 2 and 3, there is a no 5. Okay, and 2 and 3 are only a factor. Okay, 5 is not present in this factorization, right? So 6 raised to n for any value of n, they never end with 0. So by fundamental theorem of arithmetic, we can say that 6 raised to n cannot end with the digit 0 for any natural number. Now next is explain why 7 multiplied by 11 multiplied by 13 plus 13 and 7 multiplied by 6 multiplied by 5 multiplied by 4 multiplied by 3, 2, 1 plus 5 are composite number. So what is composite number? So composite number is the multiplication of prime numbers or product of prime numbers, which you learn in previous slides. Okay, by fundamental theorem of arithmetic, right? So by simplify these numbers, you got 1014 and simplify this number, you got 5045. Now I factorize them. Okay, so 1014 is factorized like this. Okay, and 5045 is factorized like this. So by observing this number, these all numbers are prime number. Okay, you cannot further divide it, right? So these all are the prime numbers. So by fundamental theorem of arithmetic, we can say that 1014 and 5045, both the number are composite because both number are product of prime factors, right, other than 1 and number itself. Okay, they have a no 1 and number itself, but other than that number you have a more prime factors. Okay, so remember composite number, it have a more than 2 factors. Okay, exactly 2 factors, then it's called as a prime number. But if it have a more than 2 number factors, okay, then it's called as a composite numbers. So we can say that these two are the composite numbers. Now example number 7. There are a circular path around a sport field. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting points? So here pink ball is like a Sonia and a blue ball is like a Ravi, that both are take a round or drive in circular path like shown in figure, right? This is your starting point, right? Now we have to find that after how many minutes it's come together. Look at that, the ball will be met at that same time, right, at some place, right? So how many minutes are required? Okay, because Sonia takes 18 minutes to complete this round and Ravi takes 12 minutes to complete this round. So it's nothing but simply you have to find the LCM of 18 and 12, okay, and verify your answer. Okay, you find the LCM of 18 and 12 and this is your answer. After that minutes Sonia and Ravi get met. Okay, thank you.